Awesome. Yeah, thanks everyone. Yes, my name is Amanda. I'm currently a postdoc at Sandia, and I just wanted to talk a bit today about setting up molecular calculations, specifically if you're driving them through Nexus. And so given what Jaren had discussed on Tuesday about the statistics, I'm going to kind of take that information and that groundwork and try to show you how you would actually set those up and probe those statistics in your own calculations. And so the goals for today are, yes, of course, how to drive calculations using Nexus, but additionally, how are we going to define our trial wave function for molecules? One piece of that trial wave function will be our Jastrow factor, and how do we optimize that, as well as some of the considerations for diffusion Monte Carlo that we have discussed so far and what those look like here in this setting. And so a bit of an outline, I've separated this by two systems. The main one we're going to look at is just going to be the beryllium dimer, which was originally a tutorial put together by Anwar Benali in 2021, but we've brought it up to date and kind of streamlined it a little bit. And additionally, once we look at all the pieces of beryllium, we want to move on to looking at a kind of more complete example. And for that, we're just going to look at the binding curve of an oxygen dimer, or O2. And finally, I'll just make a few comments at the end for some additional considerations. And so starting with the beryllium dimer, there have been previous papers. Here is one on beryllium where they looked at a bunch of various trial wave functions and the energy coming out for the beryllium atom and the beryllium dimer to calculate the binding energy of beryllium. And you can see here on either in the table or through the plot on the right-hand side, that depending on which trial wave function you use, you will get these sensitivities to that trial for even such a simple molecule as Be2. So these are DMC energies based on the trial listed on the x-axis here. And so we're just going to use this to kind of learn how to set up a calculation and probe the parameters we need to worry about. And so I don't want to assume that everyone's used any software before. And so I wanted to just kind of give an overview on what an actual input file for PySCF on its own would look like and what you will be setting up using Nexus. So on its own, you'll have just a Python script that imports the PySCF library, and you'll simply define your molecule as shown here, coordinates, basis set, any charge or spin. And once that is built, you'll come down and feed that into your calculation here, doing a restricted Hartree-Fock calculation. And in the case that you are intending to use this calculation for orbitals to feed to QMC, you'll want to export those here. So, so this is on its own, but if we want to set this up with Nexus, it's not too much work, but it does look just slightly different. And so this is one of the materials that is going to be in the workflow, or sorry, in the tutorial materials on GitHub. And so I'm going to kind of walk through this in big pieces here of just how to drive Nexus for something like just an SCF calculation. So beyond just importing your libraries, what we're going to do here is loop over a collection of basis sets and functionals and see how that impacts the self-consistent energy for beryllium. And so looping over these, we can first run a Hartree-Fock calculation. So in Nexus, we have this generate PySCF call, which is going to be fed a system that you defined here will just be that Be2 geometry. And this can be read in from an XYZ file. You can define it in this file itself. There's a few ways to do that that are pretty well documented. And this is shown in the example online. And again, we'll have this mole object like you saw in the PySCF script itself, where we, again, do basis, any symmetry considerations, or PySCF arguments that you want to provide for the system. And again, for the calculation, you'll have this calculation object that will take any arguments relating to the type of calculation you want to do. And so here we're just performing, Hartree-Fock. So the method equal ROHF. And then finally, once we have Hartree-Fock to compare to, we're also going to set up the same thing, except for this time, we're adding an argument for the exchange correlation functional. And so what these results will look like is going to look like this, where again, functionals along the x-axis, energy along the y-axis. These were, these are shown for a pseudopotential calculations, but nonetheless, you can see that we have Hartree-Fock, LDA are way out of agreement, whereas some of these other ones look like they are pretty well in agreement. And then if we zoom into the picture on the right-hand side, you can see that there is still a pretty large basis set dependence, and that the agreement is also not as great as it looks. It was just a kind of scale impact on the left-hand plot that made them look like they were in agreement. So it's a place where diffusion Monte Carlo can come in and kind of resolve which of these functionals is agreeing what is the right answer here. And so from this, we want to move on to thinking about what does this wave function look like in quantum Monte Carlo. And so it's already been discussed mostly, so just going to run through kind of the key points here for molecules that we want to think about. And so for our trial, we typically have a symmetric and an anti-symmetric portion. And today I'm just going to cover a Slater determinant for the anti-symmetric portion and a Jastrow factor for the symmetric portion of that wave function. And so our Slater determinant can be either one or many Slater determinants, but for a given determinant, you will have a separate up and down determinant. And that determinant is built up typically using a linear combination of atomic orbitals, or at least that's what we're working with today. For the example that we're going to work through first, we are going to do this in an all-electron case. And so you'll see how to apply a cusp correction. And that's, I'm not sure how much that's been covered yet, but we want to make sure that, yeah, we don't have this unphysical kind of divergence at when the electrons get very close to the nuclei. So we add a cusp correction to address that. And so the choices that we have to make are really in the how we get the orbitals and the basis set used for those orbitals. And oftentimes for diffusion Monte Carlo, we can view it as basis set independent. However, it can benefit you if you have a more accurate trial wave function. So starting with a reliable basis can be important practically. And so just an overview of what we're going to do with this molecule. You'll find a collection of files on GitHub right now. And what we're going to look at is setting up the cusp correction, which will be in the file shown on the right-hand side. And then how do we optimize this trial wave function? And also some of our considerations for DMC, which will be these last three here: Timestep, our error bar control, and our population bias. And so for the anti-symmetric part of our trial wave function, so the Slater determinant, we're just going to be dealing with a single Slater determinant. There are converters and interfaces to do multi-determinants, but we're not going to discuss that today. However, it can be important. But for today, just to focus on how to get started. So again, we'll set up the Nexus SCF object just as we did before. And in terms of how to make Nexus output the orbitals for QMCPACK consumption, that's going to be this save QMC option that you see at the bottom here. So that's going to be the key as you want your orbitals there. So once you get the output from PySCF, there will be another step in Nexus for you to take that and convert it into something that QMCPACK can consume. And so you'll have this generate for QMC call here. There are some other options that are documented for this, but for our basic case, we really just need to tell it where to look. And that it depends on the orbitals that we previously calculated. So that's what this line here is telling us. Convert for QMCPACK in general does support a number of codes, not just PySCF. And you can find those documented as well, or if you're interested in a certain software, you can check with us on how to get those. But nonetheless, so now this is all we need to do to get our orbitals ready to go. So you'll make your choice of functional and basis set it up, and this is all. So when you run convert for QMCPACK or check the output after Nexus is running, you'll get a collection of files. And right here, they just have a generic name of the C4Q. But I just wanted to show a little bit of the default output that will come out of Nexus. And so you'll get this XML file here, which again will point to your structure, the wave function, which contains the orbital information. It'll set up your Hamiltonian, as well as kind of a default set of simulation parameters. And Nexus can be used to kind of customize this and really kind of be the workhorse for you. But just know that this is being created under the hood, and you can go in and look at this to see what the XML actually looks like. And so for the anti-symmetric portion, we use a Jastrow factor to build in n-body correlations. We almost always use 1 and 2 body Jastrows. 3-body Jastrows can be important as well. And so just to kind of show what that input looks like. So for the form of J1 and J2, you can see that here on the left-hand side, where you have interactions for the one body between ions, capital R, capital I, and then the electrons here, whereas J2 will then start to consider interactions between pairs of electrons just based off their distances. And so to optimize J1 and J2, you'll again have this generate for QMCPACK call, but I want to focus in on exactly what's controlling the Jastrow in this case. So here, you'll just have these 3 terms here where J2 equal to true will initiate those 1 and 2 body Jastrows, as well as setting the appropriate cutoff. So this is the cutoff at which you are no longer considering interactions between particles outside of this cutoff. And so there are typically sensible defaults for this, but you do have control on that depending on the system that you're looking at. And finally, we want to optimize this. So how do we tell Nexus that we want to do an optimization? That's going to be here with QMC equal opt. You can select your minimization method for your parameters, as well as some of the other relevant parameters here. We can talk more about specific optimizers. OneShift is a rather quick optimizer that can usually perform quite well. The relevant parameter for that is typically this min walkers is specific to OneShift. So there are other options, and there are use cases for both, but OneShift is typically a pretty good starting point, and I would recommend that. And yes, additionally, as Paul had mentioned, you're able to define this total number of samples that you want, at least for these optimizations. And so this is what your J1 and J2 look like. J3 is not too much similar. We take a slightly different form of this Jastrow. And again, you still have cutoff parameters you need to consider. And the input call for Nexus is not too much different, as you can see here. again, just to focus in on the important bits here, is this J3 equal true will initialize a Jastrow factor with zero or coefficients with the value of 0 to optimize from. And again, the optimizer input is going to look pretty similar, with an emphasis just on the fact that here at the bottom, you're now taking that optimized J1 and J2, passing that into this J3 optimizer. And kind of just practical note is that typically when we start to optimize a 3-body Jastrow, those parameters, those correlations can impact the optimal parameters that can be found for the 1-body and 2-body Jastrow. So it's a good idea to get kind of a stable answer for 1 and 2 first, but as you're optimizing J3, you'll also want to reconsider and optimize J1 and J2 in the presence of the 3-body Jastrow as well. And this setup will do that for you. So you'll be able to see that in the tutorial. If you dig into the files, you'll be able to see these parameters changing as you go through optimization cycles. And so once you submit this and run this, you'll get a directory full of output files, these scalar.dat files, which contain your local energy and variance and a bunch of information that can be very useful to you. The simplest way is just grabbing out the energy and variance using the QMCA tool. And here, I'm just showing it in sequential order up through the optimization iterations. And what you want to consider, at least for molecules, is yes, a minimization in the energy, a minimization in the variance. And I know it was mentioned on Tuesday, but just to emphasize again that the ratio between your local energy and your variance is a very good signal of a good trial wave function. And so I think 0.02 is our like guiding value. However, or sorry, there's no however, that's like what you want to try to aim for. And if you see it's much higher than that, that can signal some issues in the kind of initial parameters you might be starting with, or initial orbitals, something like that. And if we actually want to visualize this, that's kind of how I think about things. I just wanted to show here those values I just showed on the previous page for the optimization are just shown here on the left-hand side, energy on the top and variance on the bottom for just a 1 and 2 body Jastrow, and then with the addition of the 3-body Jastrow. And you can see that through the cycles, there's, a little bit of finding the right parameters. But upon the addition of the 3-body Jastrow, first, upon the addition of the 1 and 2 body Jastrow, we see this very dramatic decrease in the energy. So it's accounting for a lot of the correlation energy just with the 2-body Jastrow. When we go on to add the 3-body terms, we do still see a reduction in the energy as well as the variance. It's less extreme, but it is still valuable to go in with this more accurate trial. And so the other thing to note, which I think has been touched on already, but I wanted to demonstrate it here as well, is that if we take this optimization and start running production calculations with the resulting trial with the optimized parameters, we can still see that going from a 1 and 2 body Jastrow to the addition of a 3-body Jastrow, we will see a reduction in the energy. By the time you get to DMC, your Jastrow factor shouldn't matter anymore. DMC should be the equivalent to having the perfect Jastrow factor. However, it can affect things like your statistics. And so you want to make sure that you're going in with something reliable into DMC. Just in terms of, 1, the efficiency, and 2, the potential impact it can have on estimators as well. And from there, now we can say that we have this optimized trial wave function. So again, with these, just to step back for 1 second, these are going to be meant to run quickly on the virtual machine. So they are not meant to be the best converged or the best statistics. They're meant to give you a flavor of how this workflow would work. For larger molecules or even for this system, you would probably want to still continue to increase the kind of scale of the calculation that you're working with here. But nonetheless, to move on to now that we have an optimized wave function, what kind of considerations do we need to make for diffusion Monte Carlo? And in the tutorial materials, you'll find a collection of 4 different files. Each of them are going to be exploring one of these kind of topics. They're, a bit intertwined occasionally, so we're just going to address them one by one, which is how this would normally work in your calculations as well. So time step error, reducing error bars, the population bias, and finally in this folder, I won't have time to kind of talk about it today, but there is also this production run that I highly recommend you go in and experiment with and try to run yourself. There's this will combine all of the appropriate parameters from these considerations and look at the impact of the trial wave function on the DMC values once you're done. So we won't go into that in detail, but it is there for you, and it is a very satisfying kind of problem to work through. There's some plotting tools as well for you to kind of visualize those results at the end. And so to focus first on just the time step considerations, what this is going to look like is pretty simple here. So again, you want to make sure that you are keeping track of what this calculation is going to depend on, such as the particles, the orbitals, the cusp correction. And so here we're going to, again, indicate we're doing a DMC calculation. We're going to start with an initial VMC to generate some of the kind of Walker configurations that we want to look at and sample from. And finally, to actually set up this time step exploration, we want, these are going to be the relevant arguments, excuse me. So the time step we want to start with, the time step factor is how much we are decreasing the time step for each run. We're going to explore 4 time steps and then the relevant kind of DMC, oops, sorry, I just want these two, the relevant DMC type parameters. So here we're defining total walkers as well as the number of blocks we want. And we're just kind of picking something at this point to explore that impact. And so once you submit and run this, what you'll see is that on the right-hand side here, we're looking at a large time step as we step down to a small time step here, and the energy, total energy here on the y-axis. And you can see that even for a small system, this choice of time step can really matter. And what is, I know has been discussed, is this red line is indicating the extrapolation to a 0 time step based on a linear fit to this data. So this can be done with Nexus. There's a QMC fit tool. And so this call up here is saying that, okay, I want to fit to the time step with an equilibrium subset, sorry, and a subset of blocks used as equilibrium here, 20, and the various time steps you feed in as your as an argument. So it can kind of extrapolate and do that linear fit for you. And so that puts out this value here and the associated error bar. And so given this, the smallest error bar we explored, this is about 0.0025. And since we're seeing this kind of dramatic impact of the time step, we're going to want to use that small time step moving forward for the DMC calculations. And so with that kind of decided, we can also go in to think about the error bars, which Paul has also touched on. In terms of that, if you want to reduce your error bar by a factor of n, you want to typically increase the blocks by a factor of n squared. There's a bit of a choice between increasing the population versus the blocks, but we're going to focus on addressing the number of blocks here. So in this file, this will be like the run 2 error bar file in the tutorial. And so the important pieces of this script, again, are going to be that we want to start with an initial block size, and then we're going to loop over an increasing amount of block sizes. And again, that's just fed in as just a variable here to the generate for QMCPACK. So in this loop, it'll generate your set of 5 jobs with increasing number of blocks. And so once you run this project in the Nexus script, what you'll end up with is the following data. Here I'm just showing for 4 sets of blocks. And so what you'll see is as the number of blocks are increasing, you will see that our error bar goes down and we're getting better statistics in describing our system in general. But this reduction in the error bar is really the important part here as well. This does come with the trade-off that as you increase the number of blocks, you're also going to be increasing the wall time here. So again, all of these will still run on the virtual machine, but as you scale up to using larger clusters and your own machines, this is something you'll have to try to balance, getting as small of error bars as possible while staying within your computational resources. And so this is, yeah, pretty simple and pretty quick to set up. So even switching over to a new machine shouldn't take too much work to try to probe your own system here. And so the last consideration, which I almost actually left out, but I know there was a question about it on Tuesday, so I just wanted to explicitly show how this would be done as well. But again, very similar to the error bars where, again, we're just starting with some initial population and we're going to increase that to a certain point. And again, you're just changing the walkers that you're doing, but you want to keep the step size, or sorry, the number of steps relative to that. So you can kind of attempt to keep the error bars on the same footing as you look at this population bias. And so those results are shown here on the right-hand side. Again, number of walkers versus energy. And again, as you increase the number of walkers, especially out to this largest one, you're seeing that there is quite, a notable population bias that you want to keep track of. And so for the production run, you'll see in there that I actually use a slightly larger population. And I think, yeah, including that in this convergence study would be useful as well. So I'll try to add that to the tutorial. But yes, increasing the number of walkers here was quite important. And again, this is just for a simple example. In a large scale calculation, you're still going to need a lot more than even what is done here. But this will be enough for us to get statistics meaningful enough for us to learn something and like compare to other wave functions or other results of similar quality from different functionals. So this will still be useful. And this is how you would probe this in your own system. And so, yeah, with that, those tutorials kind of exist within their own folder, so you can run through just the beryllium dimer example. And that was broken up into many different pieces. There is another example, which is going to be setting up, probing the binding curve of the oxygen dimer. And for that, we're no longer going to use all electron calculations. We're going to switch to using pseudopotentials. And there's just a few notable changes. These changes will be similar between molecules and solids in terms of what Nexus needs to know about, but showing here specifically for this O2, you're going to want to, in your system definition, in addition to providing the elements and the positions, you're also going to inform Nexus how many valence electrons each atom is going to have. So here our oxygen will replace 2 electrons, leaving us with 6 valence electrons. In terms of what else Nexus needs to know about is where your pseudopotentials are stored at. That could be in the same directory. It could be in some directory just for pseudopotentials as I have it set up. But you just need to make sure it knows exactly where to look. And so once that information is set up and passed, you can use this pseudopotential set to kind of have a collection under a given label. So let's say you had more than just one atom here, maybe you had 4 or 5, and you had the CCECPs for your QMC calculations, but in some codes such as Quantum Espresso, if you needed both the XML and a different format such as UPF, like Quantum Espresso uses, you could kind of collectively define them here and pass them to Nexus arguments. And that's all I wanted to show here, is that for your SCF generation of the orbitals, you'll just add the definition of the basis set that corresponds with the pseudopotential that you want to use, as well as the name of the pseudopotential family. Here we're using the CCECP pseudopotentials, and we'll also pass that same information into a generate QMCPACK call. So just making sure it knows that we want to use this CCECP pseudopotential set that we defined in the block above. So you'll see all these pieces in the tutorial as well, but I just wanted to kind of isolate them out and highlight each one of them. And so again, I don't want to just have this be a bunch of puzzle pieces you're putting together. And so in this example, what you'll see is that you'll have a set of calibration runs, and these calibration runs are going to be doing the Jastrow optimization, the Timestep exploration. You can add in an exploration of the population bias if you're interested in seeing that. It would really just be kind of a small, kind of bringing over the stuff that we did in Beryllium. But this will help us determine the appropriate DMC parameters that we want to use. And finally, then you'll have this, sorry, my words escape me. We'll have this final run that I'm calling the production run, which is actually going to do the entire dissociation curve. And here we'll have just this list of distances described. And you can see that as we loop over these distances, we redefine a molecule that has that distance. And then we'll run through all of our steps from the SCF, getting the orbitals for the given geometry, again, optimizing the Jastrow factor for each geometry, and again, going through the QMCPACK with your going through your diffusion Monte Carlo calculations with this generate for QMCPACK call as informed by your calibration runs. And so again, there are tools, post-analysis tools in the directory, and you'll be able to create a figure that looks like this, where you'll have your dissociation energy along the y-axis and your bond lengths that you're exploring along your x-axis. As it's set up now, it'll loop over a bunch of functionals to kind of see the differences in the minimum as predicted by each functional. So this will take longer to run. You could just submit it and leave it for a while. It's not meant for you to kind of sit there and get immediate feedback, but it shouldn't take a ridiculous amount of time. So just to mention, yeah, once you submit this, you don't have to just sit there and wait. You'll go make dinner or something and come back and check on it. But it's an interesting way to see how you can run just this entire kind of orchestrated calculation within a simple script that's a few, a small Python script. And that makes life a lot easier for everyone. And so from here, I just wanted to make note of some additional considerations. So the two that I wanted to touch on are how to start your own system, and also what else do we need to consider in the choice of trial wave functions, as that can be really important for molecules. And so to first address how to start your own systems, as I mentioned, these aren't meant to be fully converged calculations on these small systems that we're running. However, these scripts that we're doing are, just to simply copy and paste them and replace them with your system is a great place to at least start. Then once you have everything on your machine of interest, you can start scaling things up and working with the maybe walkers per rank versus total walkers to really make the most out of your computational resources. However, yeah, you don't need to build it up just from scratch. I think taking these materials, not only from the molecular section, but as well as the other sections that have happened, like the LIH tutorial that Jaren has done, and there's the solid state calculation one coming up next week. All of these materials can be really useful for starting your own work. And so in the spirit of that, you'll see in this folder that there's also a water molecule directory, and there's been examples around water this week, but I would encourage you that if you want kind of this crash course in doing this workflow yourself, I've just put in there the bare bones of generating the SCF orbitals. But it would be really great if you want to learn how to do this on your own, to kind of take this and bring it into, or take the pieces and bring it into this script, kind of copy them over and make the appropriate changes. They're not up yet, but I will have like reference materials so you can see kind of what the output should look like and if you're getting the right thing from these time step explorations and error bar reduction calculations as well. And so, again, if any questions come up or you're not sure how to do anything, anything like that, just feel free to reach out. My email's on like the front slide of this that you'll have access to, but yeah, we're here to help if you aren't sure how to accomplish something, but just mentioning this as a starting point. And so, yeah, the last molecular or the last specific molecular thing I just wanted to bring up, this applies to solids as well. I've had a lot of experience with it for molecules myself. And so even from this table that I presented in the beginning from this previous work, we're only exploring this small subset of possible trial wave functions. And we're only exploring those based off the DFT functional. And what you'll see is, one, that already matters a lot. So it's something that you will need to explore. However, there are going to be problems in systems, especially those exhibiting strong correlation, where the DFT functional alone isn't going to be a good enough trial wave function. The nodes are going to be too far off that your fixed node error will kind of keep you away from the results that you're looking for. And so there are other options that we won't have time to go into today. There are kind of some examples on the QMCPACK repository, as well as just reaching out to us if you have interest in these specific things. So one very common one is multi-determinant expansions. And so this kind of entire latter half of this table is all different multi-determinant expansions of different kind of cast spaces or configuration interaction type of results here as well. So in addition to cast wave functions, there's also interfacing with quantum package, the selected CI code, and that can be incredibly useful for getting a reasonable multi-determinant trial as well. That's not available on the virtual box, but it can be installed there just following the instructions that you'll find for the package. But and secondly, orbital optimization is another way in which you can improve upon the trial at the VMC step. So the parameters of your basis set can be treated as optimizable parameters in your VMC optimization, and you'll kind of do rotations between subsets of orbitals to get orbitals that should be better correlated or should capture correlation better, I should say. It's still something that's an ongoing kind of research direction, even especially for larger systems, but it can be very valuable already. And so just to summarize, revisiting the goals that we talked about before on wanting to know how to drive calculations using Nexus. I've overviewed a few systems, but hopefully once you try to do them yourselves, you either just keep going with flying colors or reach out to us for help. Our next goal of defining a trial wave function, we've shown how to get the orbitals as well as initialize and optimize the Jastrow factor. And that feeds into our next point of what do we look for in terms of optimizing that wave function for molecules, which is going to be minimization of energy variance as well as the ratio between the two. When you're running a full Nexus calculation, you will see that Nexus has an internal way of deciding which of your optimization series was optimal. And that can be very useful as well as our considerations for our DMC calculations. So with that, just to mention the next session, Paul might also mention this, but yeah, next session will be on Tuesday on solid state calculations. And so yeah, with that, if there are any questions or comments, yeah, we can chat about them now. Thanks for your attention.
Thanks very much, Amanda. I see some thumbs up coming through the Zoom. I'm keeping an eye on both the Zoom chat and the Slack for any questions. I don't see any yet, but I've got some comments and questions. So first of all, I'd really encourage everyone to try these examples and set up their own calculations. It'll be very helpful ahead of the solid state calculations examples. And also hope it's clear, as Amanda said, that the workflow system is very helpful here. You can do an entire binding curve from actually quite a short Python script. So that's quite a sophisticated workflow and a good starting point for your own work. So Amanda, one thing I was thinking about, other things people might be interested to try, and maybe actually you've got the right example here, is besides running the water molecule, I think it would probably be straightforward for people to try switching dimers here and run other things other than oxygen.
That's very true. Yeah. I think even just doing this for beryllium itself would be an interesting test, or any dimer of interest should be pretty easy to swap in and out. So yeah, very good point. And could be fun to see.
Yep. Thanks very much. All right. Well, I don't see. I just see a question has come through. Let me take a moment to read it. All right, this is a multi-stage question, so we'll allow for typing. All right, the first part. I think this is a question on the fundamentals of diffusion Monte Carlo, and I'll pass it over to you, Amanda. So why allow a variable number of walkers in the diffusion Monte Carlo simulation if the walkers are already weighted? In principle, one could have a constant number of walkers and then periodically clone walkers with small weights. Is there a disadvantage to this approach?
Yeah. So I know that there is a disadvantage, and especially so for one thing, if you already have walkers that are approaching a location and configuration space that has a high probability, you want to encourage that exploration. And so having fixed weights, I know for one thing, can kind of make that a slower process to get to. So by instead allowing a variable number of walkers, what we can do is instead kind of branch off in places that we're finding high probability for our wave function and kill off walkers where there is low probability and we don't need to explore that space anymore. And so there is an efficiency gain there. And I believe there's something else about the weighted walkers that
Uh,
I'm forgetting.
yeah, I can carry on because I think actually they were asking about
Oh, okay,
having
sorry.
weights all the way through. And this is actually a fair point because at least nominally, right, these are equivalent. Uh, so the only difference here is what's implemented in the code currently. And QMCPACK currently has a variable number of walkers scheme. And in addition, there are weights being carried around. Some other codes have got the constant number of walkers with weights scheme, and there's pros and cons to both of these. But broadly speaking, they're equivalent in terms of the final energies that you get. And I will say that we will be adding a constant walker scheme into QMCPACK because that has some advantages, particularly for GPU runs. We really want to maximally utilize all the memory on the GPUs, for example. So avoiding the need to have some space for the variable number of walkers is a particular advantage there. So it's certainly a convenience. But if you're able to have a large number of walkers so that load balancing isn't a problem, I think everything's roughly equivalent. So there's a number of other follow-up questions here. Um, uh, is there any recommendation for which orbitals are the most appropriate for QMC, Hartree-Fock or cone-sham? And if cone-sham, which XC functional?
That is a tough question, and it is just a research question. I'd say you kind of will start to get a feel for your class of molecules, like what basis sets are roughly appropriate, but it's going to depend on the physics you're after. So especially if you're interested in a very kind of delocalized electronic state, like that basis set will look very different even on the same molecule if you're only interested in kind of energy differences in another test case. So I think doing a scan like what we're starting with here is maybe one way to start to assess that. Um, and so you'll be able to run a bunch of different trials, hopefully, depending on the size of your system, or maybe some model system that captures the interactions you care about. And based on the kind of the energy minimum as well as the variance of that wave function can kind of give you an indicator on which basis sets or functionals are maybe potentially going to perform better. It's not given, but that's one way you can kind of guide your choice, at least in the beginning. But there is no set answer. I'd say Hartree-Fock are typically pretty bad, and I would recommend doing some cone sham functional as a minimum. But there's still reasons to explore Hartree-Fock. But for production, I think minimum of some cone sham orbitals is a pretty good starting place.
I'd say ultimately all these choices are testable. So run a scan of different functionals for the class of systems you're interested in running, and then you'll hopefully you'll see one there, and this is very likely, that is performing best consistently.
Yeah.
There's a couple of other technical questions that I think we can answer offline, as it were.
Okay.
And let me just see if there's any other questions. See, we have a request for pointers to material on multi-determinant and OO, and I'll make a note to follow up in the Slack with some pointers to those from previous workshops and summer school. So for example, our
Yeah.
last user meeting had a tutorial on orbital optimization. So I know that's up on the QMCPACK GitHub organization.
Yeah. I'll add those to the slide deck as well, just so
Oh,
it's in
thank
one
you.
place
Yeah,
too.
good idea. All right, so if there's any questions from anyone else. All right, I don't see any here. So we'll wrap up here, and thanks again, Amanda.
Thanks.
See everyone on Tuesday.